real-time communications for the web, and real-time for video, audio, and data streams. So imagine you could have HD video calling in your web or native application, end-to-end encrypted, peer-to-peer, and all with the help of simple JavaScript APIs, so just a few lines of code. Now, how realistic is this? Is it too good to be true? Well, let's find out. I want you to go to google.com and type in DefFest for the code. And then click video call. Anybody joining me here?
I think we can continue. I will join.
Okay, we don't have too many people in the audience. Oh, there we go. Hey, so as you can see, real-time video on a web page. There's audio too, but I have it muted. No installs, no registration, it just works. So how cool is that? Now, let's talk about how this can be made a reality in your web application. So what is WebRTC? WebRTC stands for Real-Time Communications for the Web. It's a free open source project hosted at webrtc.org, and its goal is to enable simple real-time communication capabilities for web applications as well as native apps on mobile with simple, easy-to-use APIs. The idea for WebRTC was born in Google, in the Chrome team in 2009. Google followed up with a few key acquisitions in 2010 and 11, and in mid-2011 the project was born. So really, how simple is WebRTC? Here is the chunk of JavaScript code that is the core of a peer-to-peer connection establishment. So you can see that we create a new object of RTC peer connection type, which represents a peer-to-peer connection between two clients. We call getUserMedia, and what getUserMedia does is it allows you to get access to the user's camera and microphone. And in the success callback of getUserMedia, we call addStream on the peer connection to add the resulting media stream, so audio and video track, to the peer connection. And then we create something called an offer in WebRTC terminology. So you can see pc.createOffer, and we forward this offer, this session description that we got, to the other peer. Things will become a bit clearer on the next slides, but you can see that the gist of establishing a peer-to-peer connection with WebRTC is really, really simple. Here's what WebRTC looks like on a diagram. So we have two clients, a desktop and a mobile device, and there is a peer-to-peer connection between them, over which audio and video can travel, as well as arbitrary data. So think of it as WebTorrent for a web browser. In the upper part, we have a signaling server, and the role of the signaling server is to enable the clients to exchange messages until the peer-to-peer connection is established. In the bottom part, we have a stun-turn server, and it has two things that it does. The first one is net traversal, so the discovery of the client's IP addresses. And the second part is it acts as a media relay for those cases when a direct peer-to-peer connection cannot be established. WebRTC is a tale of two APIs. On one hand, we have getUserMedia, which allows you to get access to the user's camera and microphone in the browser. Okay? Because after all, you need that picture from the camera or that audio from the microphone to forward to the other peer. On the other hand, there is the RTC peer connection API, and RTC peer connection object represents a peer-to-peer connection between two browsers, or between two clients, if we're talking about mobile. It handles all the bidirectional communication between them, and it normally has one or more media streams attached to it. So you grab a media stream from the user's camera and microphone, and you attach it to the peer connection. Let's talk about Get User Media for a little bit. Here is a simple example where you prompt the user to share their camera and then show the feed from the camera on the web page. So what's going on here? We call Get User Media and we tell it that we want an audio track and we want the video track of certain dimensions. And browser will try to oblige in terms of the dimensions, but it may not. So we may not get the exact dimensions that we requested. Then follows the success callback, and in the callback we find the video element on the page, and we attach the resulting media stream to it. And then we call video play, which causes the feed from your camera to play on the web page. And then we have the error callback, which just shows you what error occurred, if any. Now, the user experience for Get User Media varies from browser to browser, and as we did our little test with Gruvia, you've probably seen the dialogue. For example, Firefox lets you choose the actual camera and microphone that you share with the web application. Chrome simply prompts you to share your camera and microphone, and in that case, the default camera and microphone are used. But the key difference here is that since December last year, Chrome no longer allows Get User Media requests on non-HTTPS pages. So, if you want to use WebRTC, if you want to use Get User Media, you have to make sure that your page is accessed by HTTPS. It's a part of a broader move by Chrome to make the web more secure, to promote SSL or TLS, which is not always user-friendly because not everybody has an SSL certificate installed on their site, but that's the reality we have to deal with. So the bottom line is this: if you're developing a WebRTC web application, you will have to use HTTPS so that your Chrome users can use it. Now, if we go a bit deeper to the Get User Media syntax, the first parameter is a constraints object. And what constraints does is it lets you specify the parameters of the media that you want to get from the user. For example, we can request an audio track but no video track. So for example, we have a telephony application and we just want to transmit voice. In the second example, we request the audio track. We also request a video track, and we say that we want the video from the camera that's facing the user, using the facing mode constraint. And that makes sense, for example, for Android devices that have multiple cameras, and the browser will try to get the picture from the front-facing camera for us. In the second example, we limit, or rather we set the desired dimensions for the video track, and as I said earlier, browser will try to accommodate that, but if it can't, we might receive a video of some other dimensions. And the last example is the most involved. We request access to the audio track, and then we specify really precisely what kind of video we want to get. We specify the ideal dimensions, and we specify the minimum and maximum dimensions that the browser cannot violate in any case. The funny thing about Get User Media is that it's really easy to also do screen sharing with it. Doing screen sharing with Get User Media is actually the matter of supplying a certain kind of constraints to it, which are shown in the very last line. But in order for that to work, your user needs to explicitly confirm that they allow screen sharing from your web application's domain. And in order to do this, they need to install an extension in Chrome, which comes from you, and the sole job of this extension is to confirm that yes, the user wants your domain to have access to screen sharing. Or in Firefox, the user will have to add your domain to a special configuration string in the app's, in the browser's config. Alternatively, and that's how it's mostly done these days, developers just create an add-on for Firefox that does it for them. So again, we're talking about the installation. And it's important to say that the only reason why they have to install an add-on or extension to enable screen sharing is an extra security confirmation that yes, I want this domain, for example, Gruvia, to have access to my desktop to screen share. The second parameter to Get User Media is the success callback, and that's where you get the media stream if the user grants you the permissions. A media stream object has one or more media stream tracks, and the track can be either audio or video. So normally if you request access to the user's camera and microphone, you get a media stream object with 2 tracks, one audio, one video, and you can do 2 things to a media stream object. First of all, you can attach it to an audio or video element on your page, and that will simply render it. So it will show you the video if it's a video track. You can attach it to an audio element, and then you will hear the audio stream. Or you can attach that media stream object to the RTC peer connection object, and in that case, you can send it via the peer-to-peer connection to the other party. The error callback is really simple. This is what gets called when something gets wrong. For example, the user denies access to your web application to access their media devices. A user does not have those media devices, or, which is now the case with Chrome on HTTP pages, you don't use HTTPS. So let's talk a little bit more about the peer-to-peer connection between 2 clients. And here I have highlighted that connection on the overall diagram. So it's a direct connection that takes place between the 2 devices. And in order for that connection to be established, the clients need to exchange certain information about them. They need to exchange information about what IP addresses they're available at, what media codecs they support, what media tracks they're offering. Is it video? Is it just audio? Is it a combination of both? And in order to exchange this information, there exists a certain procedure, which I call an offer-answer dance, but it's by no means a formal name. And the gist of it is that the first peer creates something called an offer, and that's nothing else but a session description, which contains all this information about codecs, media stream tracks. Peer A sets the description as their local description and forwards it to peer B. Peer B sets it as a remote description and calls a create-answer method. So it creates an answer, which is its own description, sets it as local description, and forwards it back to peer A. The end result is that peer A has their own description set as local, B's description set as remote, and vice versa on the B side. The RTC peer connection object has the key methods that support this flow. The first one is the constructor. The second one is add stream, which allows you to add a media stream to the peer connection object to be sent to the other peer. Then there are create offer, create answer, set local description, and set remote description for making the flow possible, which I just showed you on the previous screen. So I just talked about those offers and answers, and what exactly are those? An offer or an answer is basically the peer's session description. And what a session description is again, that chunk of information that tells the other participant what media tracks I'm offering, what codecs I support, what IP addresses or port numbers am I reachable at. And it's basically a text, multi-line text protocol that has each line corresponding to a certain piece of information. Here's an example from a real session description that talks about audio lines. And you can see there's M equals audio, so we're talking about the audio track here, and there's a bunch of IDs, a bunch of numbers in the end, and those are the IDs of the media codecs that this peer supports. And we have a bunch of lines like this in the session description that give us all kind of information about the peer. One good thing about SDP, or session description, is that since it's a text protocol, it's a text format, basically, multi-line, you can mangle it. You can change it so that, for example, you can give higher priority to a certain media codec. If you want to use, for example, H.264 in preference of VP8 for your video, you can mangle the SDP to make the browser use that codec in preference of the other one. So we have those session descriptions, and now the question is, before a peer-to-peer connection is established, how do the peers exchange that information? And this is where you have to have a signaling server. So you have to have a server that sits between the clients and that lets them exchange the information before a peer-to-peer connection is established. And the WebRTC standard intentionally leaves out signaling to the implementation. And that means that it's your job to implement that information exchange, and anything will work. HTTP long polling, WebSockets, socket.io, snail mail, UPS delivery service, whatever. It's just going to be slow, but it will work. And we at Gruvia use WebSockets with a custom Node.js backend for that. So here's the place of signaling in the overall WebRTC diagram. So you can see that there's a signaling server in the middle that allows the clients to exchange information. And that's a separate communication channel from the actual peer-to-peer connection. Another question. How do the peers learn about their IP addresses? After all, you might have one IP address as your local host IP, your address on the local network might be something different, and your external IP might be something yet different. So how does the other peer know how to reach you to establish that peer-to-peer connection? And this is where WebRTC uses the protocol or a system called ICE, Internet Connectivity Establishment. And basically it's another server that your WebRTC application has to use, whose only job is to answer the question, what is my IP address for a given client? And the good news is that those servers exist for free that you can use. Some are provided by Google, some by other third parties. In any case, though, you have to put a list of the stun servers to use in your RTC peer connection constructor. A little deeper dive into ICE, and here you can see that there is an example of an ICE candidate in the session description, and I have highlighted in red the actual IP address and the port number. So this is the kind of information you get from ICE. Over which IP addresses and port numbers am I accessible to the other peer? And parallel to exchanging the information about session descriptions, peers also exchange information about their ICE candidates. And ICE candidate is, in a simple terms, it's just a combination of an IP address and the port number. RTC peer connection supports a number of methods and a number of events that let your peers exchange this information. So we have the event called onICE_candidate. Your WebRTC application processes it and forwards the ICE candidate to the other peer. So parallel to the offer-answer dance, we have the ICE candidate dance, where the peers exchange information about their basically IP addresses and port numbers used. In an ideal world, you can always establish a peer-to-peer connection, but we know that sometimes we have strict firewalls, we have network configurations that prohibit peer-to-peer connections from being established. And in that case, we need to use a relay. We need to use a server whose job is to forward the traffic from one peer to another one. WebRTC supports a standard called turn, and you really want to have turn servers specified in your peer connection, because otherwise the peers who have strict firewall rules will simply not be able to talk to each other. And unlike stun, you will have to use your own turn servers or use some kind of paid service. And there are a couple of important considerations. The first one is that you need to mind the traffic. You'll be paying for traffic that's pushed through those servers. And in our experience, Amazon traffic is expensive, Azure traffic is expensive too, so we use a third-party provider for that. Also, you need to make sure that for a given pair of participants, you select the optimal turn server based on the geographical distance. So you don't want two people talking in America via an Asian turn server, because the latency will just kill you. And the good news is that turn servers often double as stun, so we talk about stun and turn servers, and you also have to supply a list of turn servers to your peer connection constructor. And here's the place of the stun and turn servers on the peer connection diagram. So again, the job of those is to help in net traversal and relay media between the peers if a peer-to-peer connection cannot be established. I've been talking about WebRTC mainly in the context of video calling and audio calling, but it's important to understand that WebRTC is not just about media. It can transfer arbitrary data just as well with something called WebRTC data channels. And you can think of data channels as WebSockets, but peer-to-peer, that can also have some unique characteristics. For example, a data channel can be reliable or partially reliable, or it can be in order or out of order delivered. So if you're developing a gaming application, for example, and latency is extremely important to you, you can say that, okay, I can have a data channel with out of order delivery. So it's possible that the other peer will get messages out of the original order, but the latency will be better. And this is made possible because the underlying protocol of WebRTC is UDP, which is inherently out of order and partially reliable. On the API level, you create RTC data channel objects using the create data channel method of the peer connection object. There are really some exciting use cases for data channels, for example, peer 5, and I'm going to talk a bit more on the following slides. So I touched on the protocols, and here's the complete picture of the protocols used by WebRTC. So on the lower level, it's UDP, and UDP was chosen because, again, for real-time communication, latency is hugely important. We can live without a few drop frames, but latency is really important for us. On a higher level, we have DTLS, which is a close cousin of TLS, but the difference is that DTLS can work over UDP, whereas TLS can only work over TCP. And the job of DTLS is to encrypt communications between peers in WebRTC. And the important thing here is that in WebRTC, it is impossible to establish a non-encrypted call. So all connections in WebRTC are end-to-end encrypted. Even if a connection is relayed through a turn server, all that a turn server does is forward packets back and forth. So it does not impact your end-to-end encryption. So things are really secure there. Then we have SRTP protocol for transporting audio and video. And then we have SCTP for transporting application data. Here is the overview of the whole stack. So we have the IP protocol on the bottom. We have UDP, ICE, ton and turn for facilitating connections, DTLS, SRTP for media, audio and video, and then SCTP for data channels. If we go back to the media, how is the media encoded in WebRTC? What codecs are used? WebRTC endpoints are free to use any codecs they choose, but the standard specifies certain codecs that are mandatory to implement. And the goal here, of course, is to guarantee interoperability between different WebRTC endpoints. For audio tracks, there are two mandatory to implement codecs. The first one is Opus, and the second one is G711. Opus is a modern, free, open-source audio codec that provides excellent quality across a wide range of bitrates, so it sounds very good on 16 kilobits per second, it sounds awesome on 256 kilobits per second. G711 is a granddaddy from 1970s and used pretty much for compatibility with legacy telephone systems. On the video front, we have two mandatory to implement codecs. One is VP8 and the other one is H.264. H.264 is the industry standard. It's not a free codec, but it's widely supported in software as well as hardware. So chances are if you have a smartphone, it has a chip that's solely responsible for encoding and decoding H.264. VP8 is a free and open source codec by Google. However, it doesn't have just that much of hardware support right now. And in terms of the browsers, Chrome supports VP8 and H.264 behind the flag, and Firefox supports both codecs out of the box. So why is it important? Well, if you're developing a mobile application using WebRTC for real-time communication, you really don't want to have software encoding and decoding of video, because it will be a performance and battery hit for your application. Where is WebRTC supported today and right now? Well, the mantra that I'm now used to is that it's Chrome, Firefox, and Opera on desktop and Android. And by desktop I mean Linux, macOS, and Windows, and Android. So that means if you fire up Chrome on your Android device and go to Gruia, for example, you will be able to make a video call from your browser on your mobile device, which is not really usual for a lot of people. You can support Internet Explorer 10 and 11 as well as Safari on desktop with a plugin, and Gruia supports one such plugin called TemAssist. plugin, the WebRTC one. Microsoft Edge supports ORTC, Objective RTC. It's a flavor, so to speak, of WebRTC, a related standard, but it's not directly compatible with WebRTC. There are proofs of concept where an audio call works, but video compatibility is not there, at least for now. On iOS, no browser currently supports WebRTC. It might change in the future, I'm going to talk about it a bit later. But you can always bake WebRTC into a native application on all platforms. On Android, on desktop, on iOS, you can always build the WebRTC library so it's part of your own application. And you don't rely on the browser stack and call things via JavaScript APIs. So as I said on mobile, if you have a WebRTC web application, you can be sure that it will work out of the box in major Android browsers. You just have, of course, to make sure that the user interface will work, so some responsiveness is necessary, of course. On iOS, a native application is the only way for now, and you have a few options here. First of all, you can build the code in the WebRTC.org repository for iOS. It's not as straightforward at times, but it works, and we've done it for the Gruvio iOS app. You can use third-party SDKs like OpenWebRTC from Ericsson, EasyRTC, OpenTalk, there are a few others on the market. And with Android, if you want to have a good native experience, you can also bake WebRTC straight into your Android app. And in fact, that's what we're doing right now because we're developing a native app for Android for Gruvio. Or yet another possibility for Android, since browsers on Android support WebRTC, you can put a WebRTC application into a web view in your app. So you will have a mix of native code as well as a web application sitting in a web view solely for the WebRTC capabilities. What are the real-life challenges with WebRTC? Well, I would say that the number one challenge is that stuff just breaks so quickly. Just a few examples from December last year. Chrome 47 came out and it said, no longer will we allow get user media on HTTP pages. So it was a headache for some of our clients because we allowed to embed our Gruvio widget on third-party sites, and the sites that use HTTP suddenly stopped working. I mean, the video calling functionality stopped working. Firefox 43 came out that same month, and it deprecated some old format for RDC peer connection constraints. It's something that we had to be aware of as well. And things like this are everyday business in WebRTC land. This functionality, this technology is developing very rapidly. So using a polyfill is a good idea, which is basically a chunk of code that abstracts out the differences between various platforms, various browser implementations, and we use a variation of Adapter.js from Google. There are also a number of services on the market whose job is to test your WebRTC implementation and tell you if there's any problems with it. And TestRTC is one such service that we're aware of. Some recent developments in WebRTC. Despite having a stake in VP8 and VP9 video codecs, Google seems to be really committed in following through with WebRTC standards and supporting H.264. H.264 is now available behind a flag in Chrome, and what's really important for us, for example, is that hardware H.264 is now supported as an experimental mode in the iOS build of WebRTC. So that means that you can now try and build WebRTC for iOS, and it will use the hardware iOS encoder built into the iOS device, which leads to better battery life and much better performance, as opposed to software rendering and software encoding of VP8. Just recently, there was a big news in the WebRTC community. Apple officially placed WebRTC in the development queue for WebKit. That might mean that we might see WebRTC in Safari soon. Most probably we'll see it in OS 10 first, and then we're going to see it in iOS. And despite already supporting ORTC in Edge, Microsoft realized that not a lot of developers will go into the trouble of supporting yet another standard, given the smaller market share of Edge. And they said that we're going to support WebRTC alongside ORTC as well. So that means that hopefully in not too distant future, we will see all major browsers supporting WebRTC out of the box. How to stay in the loop? There are so many new developments in WebRTC that you really have to if you decide to implement a WebRTC application. The mothership is, of course, WebRTC.org. This is where all the code is. Some important announcements are being made. There is a page, the official specifications on the W3 org. Google Chrome Developers channel has a few videos where the WebRTC team comes in with important announcements and their plans for WebRTC. And there are a few blogs, Blog Geek Me, WebRTC Hacks, WebRTC Experiment, which talk about WebRTC and the latest developments in this area. So the question is, what will you do with WebRTC? And I have to mention that the cases here are far from the biggest services by usage that use WebRTC today, because WebRTC, for example, is used in Facebook. Facebook uses WebRTC already for video and voice calling as part of the messenger. And that Slack uses WebRTC for voice calling, which they recently launched. And I assume they will use it for video calling that they supposedly will launch. But these are instead more specific, more exciting use cases, not the straightforward ones. For example, there's Peer5 that does serverless peer-to-peer CDN. And the cool thing here is that instead of having CDN servers that serve media to the users, for example, videos, they use RTC data channels so that the viewers kind of collaborate between themselves, sharing chunks of the video via direct peer-to-peer connections between them. Thus, they offload the servers that way. There is no central CDN. There's Telebeam that does TV video calling with WebRTC. There is Ziggo that allows for asynchronous video recording on your page. So imagine you are an HR portal and job candidates can leave video responses to your interview messages right on your website. So that's what Ziggo does. Crankwheel allows for one-click screen sharing for enterprises, for example. And of course there's Groovio, which I showed you at the very beginning, and which is the world's easiest video calls. So here's a little bit of our story. The big promise of Groovio is just you agree on the code and talk. You don't need to install anything, you don't need to register or create an account. You just agree on the code, invite the other person, and the conversation begins. We launched almost 3 years ago in 2013, switched to WebRTC as I would say, one of the earlier services to switch to WebRTC in 2014. We got venture-backed last year, and we witnessed some staggering growth since launch. And you can see the number of our call minutes growing from inception. We've been covered by major media publications, and we see exciting use cases in a lot of verticals, from telehealth to real estate to language tutoring and a lot of others. So, if you are a web developer working with JavaScript, React, Redux, mobile developer working with Android or iOS, then let's talk. Shoot us an email at talent@groovio.com. And here is the picture of our office building. We're located here in Košiciach, Aston building. That was it about WebRTC. I'll be happy to answer any questions. Here are my contact details, and of course, any questions right here are welcome as well. All right, so I assume there are no questions. Thank you very much for your time. It's been a pleasure.